So today we're going to be talking about Zwitterions and how they relate to amino acids. The general structure of an amino acid is going to be the alpha carbon that is connected to the carboxyl group, the amino group, a hydrogen, and an R group. And so two of these groups, regardless of what the amino acid is going to have a titratable hydrogen, and that's going to be the amino and the carboxyl group, meaning it can lose a hydrogen or gain a hydrogen depending on what environment it is in. And then some amino acids have a titratable R group, and those amino acids are all the acidic amino acids, which are aspartic acid and glutamic acid, all the basic amino acids, which are lysine, arginine, and histidine, as well as cysteine and tyrosine. So all these amino acids have titratable R groups, but all your amino acids are going to have a titratable carboxyl group and amino group. And so depending on the pH that this amino acid will be placed in, the amino group can gain a proton or lose a proton, and the carboxyl group can gain a proton and lose a proton. And so if the amino group is to be deprotonated, the state it would be NH2, and the carboxyl group would be a COO-. If it would be in a protonated state, the amino group would have an NH3+, while the carboxyl group is COOH. So something to keep in mind here is while the amino group has no charge while it's deprotonated, the carboxyl group has a -1 charge. The amino group, when it's protonated, has a positive charge while the carboxyl group doesn't. So it's kind of inverse, but as long as you keep these rules straight, you should be fine for titrating the carboxyl, the amino, as well as any R groups that are titratable. And so when we're titrating them, there's two values we want to compare. The two values are going to be the pH and the pKa. So the pKa is a static characteristic of the molecule, and so it's not going to change regardless of where we put it. If we put it in acidic, in a basic, in a neutral, the pKa is going to be a static characteristic. And so the thing we can change is going to be the pH. We can make the pH more basic, we can make it less acidic, more acidic, less basic, and we can play around with it. So this leads us to three possible conditions. And so the first condition is going to be when the pH is going to be less than the pKa. And so the pH is a more acidic environment compared to the pKa, so we're going to result in a protonated state. The second possible condition is going to be where the pH is going to be greater than the pKa. And so now the molecule is in a more basic environment relative to the pKa for that titratable group, and we're going to be in a deprotonated state. And the last situation is going to be where the pH is equal to the pKa. And that's going to result in equal protonated and deprotonated states. And so one thing to clarify when we're in condition 1 or 2, when the pH is less than the pKa or if it's greater than the pKa, when we're talking about the protonated state and the deprotonated state, we're talking about the major state. And so this is a ratio between the protonated and the deprotonated, or the deprotonated and protonated, however you want to look at it. But it's a ratio between the two. And so in the case of 1 and 2, the major ratio is going to consist of the protonated state, while the major ratio for the second condition is going to result in the deprotonated state. And so if you have situation number 3 where the pH is equal to the pKa, you're going to get both equal protonated and deprotonated states, or 50-50. And so let's place this into application. Let's do a practice problem where we're titrating the group. And so what we will be titrating is going to be aspartic acid, that is just drawn in its neutral state. It hasn't been titrated yet. And so again, what we're doing is comparing the pKa's and the pH's. So the pKa's of these groups can be found in the back of your textbook. And so the pKa of the carboxyl group is going to be 2.09. The pKa of the amino group is going to be 9.82. And then the pKa of the R group, again, aspartic acid is going to be one of our acidic amino acids, so it has a titratable R group. It's going to have a pKa of 3.86. And so if we were to place this molecule in biological pH at 7.4, we can now titrate the groups accordingly. And so we'll take each individual functional group and titrate it individually to get the overall Zwitterion. And so when we're looking at the carboxyl acid, we see that the pKa is 2.09 and the pH is 7.4. And so this falls under situation number 2 where the pH is greater than pKa. And since this is a carboxyl group, it's in a more basic environment, and so it's going to lose the H. and it's going to have a negative charge for that functional group. Then we'll do the same thing for the amino group. The pKa is 9.82, but the pH is 7.4. And so in this case, we're under situation number 1 where the pH is less than the pKa. And so this amino group is going to be in the protonated state. And again, remember the protonated amino group is going to be NH3. So this is going to gain a proton. And then we'll do the same thing for the R group. In this case, this R group looks similar to the carboxyl group, so it's going to follow those rules. The pKa is 3.86 and the pH is 7.4. So we're in situation number 2. And so it's going to be in the deprotonated state. So the R group is going to lose its hydrogen and it's going to gain a negative charge. And so this would be our overall Zwitterion for aspartic acid at the pH of 7.4. And so if we were to calculate the overall charge of the molecule, we would just add up the charges. So we've got a -1, a +1, those two cancel out, and then you end up with negative. So the overall charge would be -1.